Okay, so in this video, we want to consider our second fundamental vector operation, which is the cross product. The main difference between the cross and the dot product is the following. If you dot two vectors together, the result is a real number. If you cross two vectors together, the result is another vector. And another really big difference between the dot and the cross product is if you dot two vectors, the vectors can be in R2, in R3, in R4, in Rn for any n, but dot product is always defined. The cross product is only defined in R3, and we'll find a way to make it work in R2, but beyond R2 and R3, the cross product does not work. Let's start with the cross product in R3. So if you remember, R3 is the three-dimensional space, and we have three fundamental vectors. There's a vector I hat, which gives us the x-axis, so it's the vector 1, 0, 0. There's the vector j hat, given by 0, 1, 0, so this vector gives us the y-axis. And there's a vector k hat, which is 0, 0, 1, which gives the z-axis. So suppose we have two vectors in R3, say u and v. Here's how we define and denote the cross product. So suppose vector u has coordinates u1, u2, u3, and vector v, also in R3, has coordinates v1, v2, and v3. The cross product is denoted by u and across v, and the way it's written down is as a determinant. Determinant of, and here's where it's a bit strange. The first row will not be actual real numbers, they'll be vectors. So it'll be vector I, vector j, vector k. And then the second row now are actual real numbers. They'll be the coordinates of the first vector, so vector u, so u1, u2, u3. The third row, the coordinates of the second vector, v1, v2, v3. And when you think of this determinant, think of using cofactor expansion along the first row. So you're going to have I times C11, J times C12, K C13. So what you have is C11, usually you write the scalar in front of the vector. So this is C11 times vector I plus C12 times vector J plus C13 times vector k hat. But if you think of it, I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. So if you add these three vectors together, the result is a vector whose first component is the cofactor C11, second component is the factor C12, and third component is the factor C13. And this is how you find the cross product between two vectors. The three cofactors of the first row of this matrix. Let's do one example, and then we are going to consider the properties of the cross product. And as you can see, the two vectors were vectors in R3 with three components. Their cross product is also a vector in R3 with three components. So, suppose that vector u is given by 1, negative 3, 2, and vector v is given by 4, 1, negative 1. Then their cross product, so u cross v, determinant of ijk, second row is the coordinates of vector u, third row coordinates of vector v for 1, negative 1. We know this is C11. Well, C11, 1 plus 1 is 2, negative 1 squared is 1, so there is no negative sign. And we find the determinant after deleting the first row, first column. So this is the determinant of this 2 by 2 matrix. determinant of negative 3, 2, 1, negative 1. That's C1, 1. C1, 2 now, and here's where you have to be careful. 1 plus 2 is 3. Negative 1 cubed is negative 1. So we'll have a negative times the determinant obtained from the given matrix after we delete row 1, column 2. Delete row 1, column 2, and the matrix is 1, 2, 4, negative 1. And finally C1, 3, sorry. 1 plus 3 is 4. Negative 1 to the 4 is 1, so there's no negative here. Times the determinant after deleting the first row, third column, which gives us 1, negative 3, 4, 1. This is the cross product. Of course, now we'll compute these 2 by 2 determinants. This is the easy part. As you remember, AB minus BC. So we'll have here 3 minus 2, which gives us 1. Negative 1, negative 8 is negative 9, but we negate this, so positive 9. 1, negative 12 plus 12 is 13. So if you cross the vector 1, negative 3, 2 with the vector 4, 1, negative 1, you get 1, 3, 1, 9, 13. And that's a cross product. So you see it's fairly simple. But as you can see, it only works for vectors with 3 components, vectors in R3. Let's ask the question now, could we make this work with vectors in R2 with only 2 components? The answer is yes, but we need the idea of embedding. Let's recall what R2 is and what R3 is, right? And you'll see with a simple observation, we will then extend the cross product to also vectors in the 2-dimensional plane. So R2 is the set of vectors with 2 components, so x, y, where x and y are arbitrary real numbers. R3, you can visualize the 3-dimensional space. All these axes are perpendicular, and we usually denote this as the x-axis, this as the y-axis, and this as the z-axis. We'll always use this coordinate system. So the x-axis, y-axis, z-axis, you can imagine the y and the z-axis being on the page, and they're perpendicular to each other, and the z-axis sticking out of the page in a 90-degree angle. So this is the 3-dimensional space R3. And again, the set of vectors or points with 3 components, x, y, and z, where x, y, and z range over all real numbers. And you may ask, well, is there a copy of R2 inside of R3? And if you look at R3, the 3-dimensional space, R2 is just the xy plane. But the xy plane is in R3 as long as the z component of the vectors of the points is equal to 0. If you have a 0 z component, then your vector or point lies in the xy plane. So when you have a 0 z component, you really have a copy of R2 in R3. And this is the natural notion of embedding. There is a copy of R2 of the xy plane in R3, and that is the set of points in R3 with 0 z components. So we use the following notation for embedding. We use this funny looking arrow, and this means embed. And embed, if you don't know this term, means that something is living inside of something. So here the R2, the xy plane, is living inside of R3, being the set of points with 0 z coordinates. And the embedding is as follows. We'll leave the x and the y coordinates the same. If we want to be in R3, we have to add a z component, and we add, if we want to be in the xy plane in 3-dimensional space, we have to have no z component, so we add a 0 z component. And this is a subset of R3. And now we can think of R2 being the subset of R3 with a 0 z component. And this is exactly the xy plane living in R3. So suppose we wanted to cross two vectors in R2, all we do is we embed the vectors in R3 and then find the cross product. Let's do a simple example of this, and this will be useful later on as well. But beyond this idea of extending the dot product, not the dot, but the cross product to R2, that's the best we can do. So we have the cross product for R3 naturally, and by embedding a copy of R2 in R3, we can cross vectors in R2. So let's do an example. Suppose we wanted to cross the following two vectors. U says the vector 4, 5 in R2, and V says the vector 7, minus 2. If we leave the vectors like this, we can't cross them, but if we embed each vector in R3, and here I will abuse notation, I will rewrite U again, and if we view U as a vector in R3, it is the vector 4, 5, 0. And if we view V as a vector in R3, it is the vector 7, negative 2, 0. And now that we have vectors in R3, we can cross these two vectors. So U cross V, as before, is the determinant of the first row being the three fundamental vectors, I, j, k. U is 4, 5, 0. V is 7, negative 2, 0. And now we can cross our vectors. This is C11, C12, C13. And as you'll see, we'll get a surprisingly simple vector. C11, delete row 1, column 1. So the determinant of this matrix, but this will give you 0, minus 0, and you have a 0x component. C12 will have a negative of the determinant after we delete row 1, column 2. But then you'll have 0, minus 0, which is also 0. And finally, C13, delete row 1, column 3, no negative sign, 1 plus 3 is 4, which is even. Delete row 1, column 3, and now you have 4 times negative 2, negative 8, negative 7 times 5, negative 35, negative 35, negative 8, negative 43. And what you notice is, by crossing two vectors in the xy plane, in our three vectors with 0z components, what you obtain is a vector that is perpendicular to the z-axis. It has a 0 x and y component, but a non-zero z component. And you may wonder, is this a coincidence? And the answer is no. This will always happen. So now, let's go back to the definition of the cross product for vectors in R3 and ask, as always, what are the properties of this new vector operation? So if we have two vectors in R3, so U cross V is the determinant of I, j, k. Second row is the coordinates of vector U, U1, U2, U3. Third row, coordinates of the second vector, V1, V2, V3. And all these properties can be really easily verified either by cranking out the cross product in both cases, or simply by remembering basic properties of the determinant. So let's start with property A. What if we U cross U and V? And what if we ask, what happens if we cross V and U, if we change the order of the cross product? Well, that would be equivalent to swapping row 2 with row 3 in this determinant. But if you remember, if you interchange two rows of a matrix, the determinant becomes negated. And this happens for the cross product. So U cross V will be the negative of V cross U. If you wanted to prove this, compute this directly from the definition, compute this directly, and you'll get the same vector. But remembering properties of the determinant, this is a very natural operation. Property B. What if we did k times the vector U cross V? Well, this would be the same as doing the vector ku cross the vector V, which will be the same as doing u cross the vector kv. And this is true for all. The inverted A symbol means for all real numbers k. The third property, so property C, what if we cross a vector with itself? If you recall the dot product, if you dot a vector with itself, you obtain the norm of the vector squared. But what if you cross a vector with itself? Well, think about it. Then the second row and the third row of the matrix would be the same. If you have two rows that are equal, the determinant is 0. But here it's not the 0 real number, but the 0 vector. We can extend this to vectors being parallel, because we know that if one row of a matrix is a multiple of another, we can perform a row operation by subtracting the proper multiple, and then we get a row of 0, and so the determinant is 0. So if you cross u with a vector parallel to it, and of course a vector parallel means some multiple of the vector u, right? Because vectors are parallel if and only if they are multiple of each other, and this will be equal to also the 0 vector. If you want, u cross v is the 0 vector if vectors u and v are parallel to each other. You may ask, how does the cross product behave now over an addition or a subtraction of vectors? And in that respect, it behaves like the dot product. So if you did u crossed with, say, v plus w or v minus w, you could actually distribute. This would be u cross v plus or minus u cross w. And those are the properties of the cross product. And again, proving those is quite boring. You have the two sides of the equality, compute both sides, and show that you have the same vector in each case. A question that we can ask now is there a relationship between the dot product and the cross product? And the answer is yes. There are two fundamental relationships. Let's look at one of them now. If we have v cross w, so if we cross two vectors, we have another vector in R3, then we could dot this with a different vector and ask, well, what comes out of this? So what if we let u, v, and w be three vectors in R3? So u, v, and w be three vectors in R3. What we now have will be called the scalar triple product. It is not an obvious result, but it's a direct calculation. So verifying the following result, again, expand both sides, the left and the right hand side, and you'll see that you'll get the same result. So this is called the scalar triple product. Scalar means that the result will be a scalar, therefore a real number. Triple means it involves three vectors, and product because this will involve the dot and the cross product. So if you take u, which is a vector in R3, and you dot u with the cross product of v and w, this is a real number, right? Because v cross w is a vector in R3. U is a vector in R3. If you dot two vectors, you get a real number. What's kind of really nice is that this operation, it's called the scalar triple product, is actually the same as the determinant of the matrix whose first row are the coordinates of the first vector. The second row, the coordinates of the second vector, v1, v2, v3. And the third row, the coordinates of the third vector, w1, w2, w3. So again, this is, without this, if you ignore this for now, this is called the scalar triple product of u, v, and w in that order. And it has actually it happens to be equal to the determinant of this matrix. And once again, the proof of this I'll leave up to you. Compute this, and you'll get the two sides being equal. Now, this is nice in itself, but there's a really nice consequence of this result. And here's the following consequence. And that is, if you cross two vectors together, and if the two vectors are not parallel, and they're not zero, the vector you'll obtain will be automatically orthogonal, perpendicular to both initial vectors. And the proof will use this result. So here's the picture of what I've just said. Suppose you have two vectors. I'll keep this up. Suppose you have vector u that looks like this. These are vectors in R3, and you have vector v, say, like this. A second vector in R3. They're both non-zero vectors, and they're not parallel. And you ask, what if I crossed u with v? How would that vector relate to the two initial vectors? And the answer is, it actually is perpendicular to both initial vectors, u and v. So when you cross two vectors together, the third vector you obtain is perpendicular to the first vector u, and simultaneously the second vector v. And this will really be useful, as we'll see in later problems. How do we prove this? Well, we'll prove this using the scalar triple product being equal to the determinant of this matrix. So here's now the fact that we've just stated. If you have two vectors that are in R3, and you cross them, automatically u cross v is perpendicular to u and perpendicular to v. So u cross v is orthogonal to u, and u cross v is also orthogonal to v. And this is a really, really useful property of the cross product. Whenever you cross two vectors together, u and v, the third vector you obtain, the cross product, is always orthogonal to the two original vectors. We'll prove that u cross v is orthogonal to u, and then you can prove the second property, that v is also orthogonal to u cross v, and the proof is exactly the same. How do we prove that vectors are perpendicular? If you remember, that's using the dot product. Two vectors are orthogonal if and only if they have a zero dot product. So let's dot u with u cross v. But if you notice, this is exactly the scalar triple product. So we now use this equality. U dot u cross v is the determinant of the matrix whose first row is given by the coordinates of vector u, whose second row is given by the coordinates of vector u, and whose third row the coordinates of vector v. And why is this equal to 0? Well, if you just look, the first and second row are the same, so we can do row 1 minus row 2. This will change the matrix, but not the determinant. And so what are we left with? Well, the first row becomes a row of 0, and we're left with the second and third row as they are. But of course, now if you find this determinant, you use cofactor expansion along the first row, and you get 0 plus 0 plus 0, and so the result is equal to 0. And because the dot product between u and vector u cross v is equal to 0, automatically the conclusion is that the two vectors, u and u cross v, must be perpendicular to each other. Proving this will give you v dotted with u cross v, and in the first row will be v, the third row is v, do row 1 minus row 3, and you'll have once again a row of 0, therefore a determinant of 0. So always keep this in mind. You have the scalar triple product. If you dot u with v cross w, determinant of the matrix whose rows are the vectors in the right order. And if you cross two vectors together, u and v, the new vector u cross v will always be perpendicular to both original vectors. And that is the cross product and its relationship with the dot product. In our next video, we will consider one more connection between the dot and the cross product, and that connection with the scalar triple product will allow us to solve problems of areas and volume as well.